Hello and welcome to Quick Precalculus Review for Calculus Part 19, also Part 5 of Unit 2. Unit 2 with these topics which I'm putting together in the context of the compound interest formula. Here is the compound interest formula. In Part 1 of Unit 2 we used this formula to solve a basic compound interest problem. In Parts 2 and 3 we thought of a and p as being variables, and this defining a as a function of p. We treated the r, n, and t as being constants. We took r to be 8% or 0.08, n to be 4, quarterly compounding, and t to be 10 years that you leave your money in there. In Part 4 of Unit 2 we change our perspective a bit based on this entire line that you see here. We thought of the function this way, where b ultimately is c to the n, where c is 1 plus r over n, therefore b was 1 plus r over n quantity to the n power. When you look at this expression, what we did in the last video, Part 4, was we treated b as the variable. You might be tempted to think that t is the variable here, but no, we took t to be 10, we took p to be 1,000. We really had the function 1,000 times b to the 10th power. We called it g of b. This is a function of b. And we used that function to solve a problem where we wanted to figure out r, the interest rate necessary to double our money in 10 years when we compound quarterly. In this video, we're going to change our focus a bit. Two questions we want to address. First, what happens if you don't do quarterly compounding? How are nominal annual interest rates related to each other when the number of compounding periods is different? What if we did monthly compounding instead, where n is 12? We'll think about that. There's also a question that I'm calling a side issue. It's an important issue, but it's a little bit away from our main focus, so I'm calling it a side issue. What does it mean to raise a positive real number to an irrational power? Not a rational power, but an irrational power like pi, for example. That's what we want to think about. Why am I doing that? Well, a number of reasons. One is it is an important issue, like I said, still, to think about a little bit. Secondly, we're going to have a little fun with it in Mathematica. I'm going to show you something kind of neat. Third thing is it is kind of abstract and difficult, and it will prepare us for thinking about logarithmic functions, which are more abstract and difficult. Very first thing I want to do, though, is I want to go back to the animation I showed you at the end of the last video, down here, to think about the family of power functions a times x to the p, where a and p are positive parameters, so this is a family of functions of x. Its inverse function, the generic family of functions that represent the inverse functions for each fixed a and p are defined by this formula, which are also power functions. Here's how you enter those functions in Mathematica. Notice the subscripts are used to emphasize that a and p are parameters that are ultimately going to be animation parameters that you see down here. Let's go ahead and enter this code to remind ourselves what it shows. The red graph is the graph of g, the original function, a times x to the p. The blue graph is the graph of its inverse. You can see this 45-degree line, y equals x, is the reflection line. You can get the graph of the inverse function by reflecting the graph of the red function across that green line. That's what's going on here with this visual. Lambda is one of the animation parameters that is causing those points to move, and also causes the blue graph to turn purple when they get close enough. There we go. Now the blue graph is purple, here it's blue, now it's purple. That's kind of fun. A and p are again parameters in the function a times x to the p. I can vary those as well. One thing I did new for this video that I didn't do in the last is I'm allowing p to go less than 1, and in that case when p goes less than 1, watch what happens. The original function looks like the graph of the original inverse function. They still have the same reflection property across that line, y equals x. These are all power functions. They all have similar kinds of graphs. Alright, I want to spend a little time explaining the code, just to remind you of some things. I'm not going to spend much time on this. If you haven't learned about this code, then you're probably going to want to skip ahead a few minutes. Manipulate again makes the animation. A, p, and lambda are the animation parameters. They are inside the manipulate but outside the show. Show, once again, combines different graphic objects. The first object we create is a plot of g, g inverse, and the line y equals x colored differently, red, blue, and dashed green. Okay, so that's making the plot of the graphs themselves. I had in the last video another line here with parametric plot that I deleted because I did not need it if you wrote that down from the last video, but I do need this parametric plot if I want to have that effect of changing the blue graph to purple at the end. It involves the if command. If lambda, the parameter that does the animation of the reflection, is less than 0.97, this plots a point way out at coordinates 100,000, 100,000. Otherwise, when lambda is close to 1, we plot a point whose coordinates are these two things, which are points on the graph of the inverse function. It's the purple graph that you see at the end. I actually could have certainly done these differently. I could have done this as t and this is g inverse, but this does emphasize that the coordinates of g and g inverse are swapped by doing it that way. This list plot, that makes, combined with table, that makes the dots that you saw as I varied lambda, and table combined with graphics combined with line makes the lines that you saw. I'll go ahead and enter it again to remind you of what you saw. If you're not so interested in this Mathematica stuff, don't worry about it, because the rest of this video is going to focus on math, although there's one thing in Mathematica we're going to focus on that's really neat. We're coming now to this related question related to this last animation. In fact, in the animation, p was always a rational number. The computer is storing numbers as rational numbers. But what if p is not a rational number? What does it even mean to raise a positive real number to an irrational power? Well, hopefully you remember, first of all, what it means to raise a positive real number to a rational power. I'm going to let m and n be positive integers, 1, 2, 3, 4, 5, 6, etc. M over n then is a generic rational number. It's a fraction. What does it mean to raise b to the m over n power? What's the unique real value of this? We're going to ignore complex values if you know about those. There's two ways you can think about it. You can either use this equation to define it. B to the m over n power is the nth root of b to the m, but that also happens to equal the nth root of b raised to the m power. And you can check it with examples if you like. For example, 2 to the, let's say 4 to the 3/2 power. That's the same as the square root of 4 to the third. 4 to the third is 64, and the square root of 64 is 8. You can also think of it as the square root of 4 raised to the third power. Square root of 4 is 2, 2 to the third is 8. You get 8 either way. So you can check that out. Alright, but what about an irrational power? What it would mean, for example, to raise 2 to, for example, the pi power, which you can type into Mathematica like this. Well, if you just enter it as is, it comes back as 2 to the pi, which, by the way, you can get the symbol pi by doing escape, p escape in Mathematica. It creates the symbol pi. Well, maybe we should first know what pi is, approximately. N will help us calculate pi to any number of decimal places that you want in Mathematica. Yes, any number, even, for example, 10,000 or 100,000. Very quickly, there's 100,000 decimal places of pi. It does slow down if you get too high, but theoretically it could do any number of places. That's the fun thing I wanted to show you. What's an approximation of 2 to the pi? Let's go say just 20 places. It's approximately that. Why? Okay. Let's go back to our approximation of pi. Let's just do 20 places for that. Essentially, to get the meaning of 2 to the pi, it's a limiting process, which is a theme in calculus. You first raise 2 to an approximation for pi, which is a rational number like 3.14. However, if you type it in as 3.14, it only gives you like 5 decimal places, or 5 decimal places there. That's just Mathematica's convention when you don't have an exact number here. You don't have a fraction, you have a decimal in there to begin with. So to get 20 places, for example, you'd have to replace 3.14 with 314 over 100. A fraction like that, that's going to give us 20 decimal places now. Is that 20 decimal places? Yeah, it looks like it. Okay. If I want more, and you can see it's fairly close to the true answer, or the better approximation at least. They're both 8.82 to 2 decimal places. What if you wanted more decimal places? Well, you use more decimal places for pi. 3.14159. So do a 159 and add 3 zeros here. That should get us a better approximation for 2 to the pi. 8.82496. Okay, that matches up to 8.8249. Let's go one more. Let's add 3 more decimal places here. 265 and add 3 zeros here. Now we have a match out to, it looks like 8.8249778. Okay? So you're getting better and better approximations for 2 to the pi. In each case here you have a rational exponent. So this is really like the, what would this be? The 100 millionth root of 2 to the 314,159,265th power. Okay? Mathematica can compute that very quickly. Pretty amazing. All right, on to thinking about relationships between different interest rates for a different number of compounding periods. If I can find it here. do I have that? Here's example. Okay, here it is. Here's example 2 from the last video. The question in the last video I've now labeled part A. I now have a part B and a part C. Okay? I'm going to be showing you some work that is going to be explaining the answers to these things. Okay? You're going to want to pause the video when you need to. You're probably going to want to take notes, and you're going to want to listen really, really carefully. Okay? So the first question, okay, you deposit $1,000 and you want it to double to $2,000 after 10 years. The question from the last video that we answered is, what nominal annual interest rate R, compounded quarterly, is necessary for such growth? The first 3 lines that I have down here in red, blue, and magenta address that. The first one, and the second one, helps us solve the problem. The answer was about 6.99% in effect. But this explains it. To answer part A, what value of R, compounded quarterly, is necessary for such growth, we need to plug in 2,000 for P, 1,000 for A, n equals 4, and t equals 10. So ultimately we want to solve for the value of R that makes this equation true. Alright, that's what we're trying to do. In terms of that alternative representation of the exponential of the power function, the compound interest formula as a power function, that's equivalent to asking what value of B will make this equation true. B was equal to 1 plus R over n to the n power. In fact, n was 4, so B was equal to 1 plus R over 4 to the 4th power. We solved this equation first by finding the inverse function of 1000b to the 10th, and ultimately, in general, we found the inverse function looked like that, which when we plugged the numbers in gave us that B was about 1.07177. That then helped us find R at the very end of the last video to be about 6.99%. What does this mean? That's what's in magenta here. Think carefully with me. This means that when interest is compounded quarterly, the nominal annual interest rate that will give a doubling time of 10 years is approximately 6.99%. The fact that B is 1.07177 means also that the annual percent change, called the annual percentage yield or APY of this account, is approximately 7.18%. 1.07177 minus 1 is 0.07177, approximately 7.18%. B I called the growth factor. It's the amount the money grows by every year. You're compounding 4 times a year. What percent do you grow by every 4 compounding periods? It's about 7.18%. Your money grows faster than 6.99% when you compound more than once a year. To solve for part B, to find the value of R that gives equivalent growth when money is compounded monthly, you need to solve this equation for R, where now instead of a 4 I have a 12 for n. I do the same kinds of things. In fact, it's the same value of B as before, the 1.07177, that stays the same. But solving for R is different now again because n is 12 instead of 4, and you get a different number, about 6.95%. So an interest rate of 6.99% compounded quarterly is approximately equivalent to an interest rate of 6.95% compounded monthly. And finally, here is the relation between the two interest rates. This equation must hold. R quart represents the quarterly interest rate. The annual interest rate compounded quarterly. R month is the annual interest rate compounded monthly. These two equations must be equal for equivalent rates. That ultimately leads you to solving for R month to be this relationship to R quart, which you can calculate and confirm is approximately 6.95%, like I solved for up here. Let's see, where is it? Right here. 6.95%. Okay? Take the time to think about that. It's a mouthful, and you'll get a lot out of it.